Hello and welcome to another video in the Introduction to Windows Forensics series. This time we're going to take a look at NTFS file timestamps. This video is going to be divided into several sections. First, we'll cover the basics and talk about how NTFS stores timestamps associated with files. Secondly, we'll see those timestamps in action on a Windows 10 VM. Next, we'll use an anti-forensics tool known as Timestomp to modify a file's timestamps. Then we'll use a tool called analyzeMFT to find evidence of time stomping. And lastly, we'll take a look at something interesting I recently discovered with regards to how these timestamps work when using the new Bash on Windows or Windows Subsystem for Linux WSL feature, or as I like to refer to it, the feature that almost makes Windows usable again. So you'll notice that I've got a Mac Times article pulled up here on the Forensics Wiki, which is a website I've used in several of my previous videos. I'll make sure and include a link to this article in this video's description, but this provides a good overview of what we're going to be talking about. It defines the timestamps used by NTFS, talks about time resolution, access time updates, and some caveats around that, and then there's a handy table at the bottom that actually contains a list of conditions and the associated timestamp behavior for 3 of the 4 timestamps that we're going to be talking about. So it turns out that NTFS is actually a pretty complex and robust file system. It keeps track of a large amount of metadata, including any given file's creation, modification, access, and entry modification dates and times. These timestamps are commonly referred to as MACB times, or MACB, with the M standing for modification, the A standing for access, the C standing for MFT record changes, not creation, and the B standing for birth or creation. NTFS is one of the only commonly used file systems that tracks file birth and creation times. So that's pretty straightforward, but you may also see these 4 values abbreviated as MACE, M-A-C-E, because why have just one name for something? MACE stands for modified, accessed, created, and entry modified, respectively. Now don't confuse these timestamps with, for example, a Linux or Unix operating system. In those OSs, there is no MACB, only MAC times, which are derived from structures called M time, A time, and C time. Those entries mean modification, access, and metadata change. The biggest difference is that there is no birth or creation time, and the C refers to changes to the metadata associated with a file, not the file's contents. This would include things like changes in ownership or permissions. Okay, I promise we're almost done with the boring part, but the next thing you need to know is that the timestamps will actually be stored within a file called $MFT, which is a Windows NTFS metadata file located in the root of an NTFS volume. As a side note, all NTFS metadata files will start with $. $MFT is probably the most important of those because it keeps track of all of the files on disk, as well as those timestamps we just looked at, as well as permissions and ownership information and more. In fact, in some cases, if a file is small enough, the actual contents of the file itself will be stored in the MFT. This is referred to as resident data, but we'll save that for another video. The interesting thing is that there is more than one copy of this set of 4 timestamps that we just looked at stored within the MFT. The one you most commonly interact with when you're looking at files with Windows Explorer or cmd.exe or PowerShell is called $standard_information. Most of the programs you run in Windows will also use this particular attribute. However, there is another copy of the timestamp stored in an attribute called $file_name. Now, for shorthand, $standard_information is commonly referred to as $SI, and $file_name is commonly referred to as $FN. The important part is that $FN is only modifiable by the Windows kernel. This means that when a SCID or SCIDI decides to use Timestomp or some similar anti-forensics utility to modify or backdate timestamps on files, we should be able to easily detect this by comparing the timestamps in $SI to those within $FN. Along that same line, there's a great presentation from Trustwave here called I'm Your MACB Daddy. I believe this was presented several years ago at one of the DEF CONs. If you look at the presentation, it will cover the basics, including what we just talked about as far as MACB, and then it talks about these 2 sets of timestamps stored within the MFT, standard information and file name. And as you can see here, it even says file name can only be modified by the system kernel. There are no known anti-forensics utilities that can accomplish this. So I'll link to this presentation in the video's description. I would highly recommend you review this after you've watched this video as well. Now for the remainder of the video, we're going to be in demo land. We're going to actually look at all of this on a Windows 10 VM and see what we can learn. So let's go ahead and switch over to our Windows 10 box next. Okay, so here we are in our Windows 10 VM. If I can direct your attention to the table in the top right, you'll notice we've got some common file operations along the left side: create, modify, copy, and access. And across the top, we've got 3 of the 4 timestamps we covered: modified, which is M, accessed, which is A, and birth or created, which is B. For simplicity, I've left out the C for changed, which indicates MFT entry modification, and also because Windows Explorer can only show these 3 timestamps, which I have turned on and in the same order. What we're going to do is walk through each of these file operations and verify that the table is correct and that what we see is what we get. On the desktop, I've got a folder called MACB, which is currently empty, and I've got it pulled up right here in Explorer. I'm going to click in the address bar and type in CMD, and I'm going to create a file called newfile.txt, put some gibberish in it, and then go ahead and save the file. So in Windows Explorer, we can see newfile.txt, and we see 3 timestamps, all of which are set to the same value of 1:40 a.m. on 8/12/2017. This is expected, of course, because it's a brand new file, and all 3 of the timestamps, according to this table, are supposed to be updated. In this case, updated to the value at which the file was created, which is 1:40 a.m. So now let's modify the file. So we'll double click on it and just add some additional gibberish to the bottom. Let's go ahead and save it. And now we notice the modification date changed to 1:41 a.m., but date accessed and date created did not. If we look at the table, according to this, the modified timestamp is supposed to change, but not accessed or created. This is exactly what we see, so that follows the table. But this begs the question, why didn't date accessed changed? After all, we just accessed the file to update it, didn't we? Well, the answer is because of this particular registry key, which is present in Windows Vista and later. It's called NTFS Disable Last Access Update, and is set to 1 by default, which indicates that it is in fact disabled. That would indicate that date access timestamps are not tracked on Windows Vista and later. Now, that does not mean that date access will never be updated. It is updated under certain circumstances, but for our sake, if we're just working with files in Explorer and actually double-clicking on them to open them like this, it isn't actually going to change that particular timestamp. We'll cover some more advanced use cases in later videos that explain when that particular timestamp is updated. So next, file copy is our next operation, but we're actually going to perform this in 2 different ways. We're going to use Windows Explorer to copy a file, and we're going to use cmd.exe to copy a file and see if there's any difference between the 2. So first off, with Windows Explorer, let's go ahead and right-click on newfile.txt and click copy, and let's go ahead and paste a copy in the same location. Of course, it appends -copy to the end, but we'll just go ahead and call it new file 2 for simplicity. And there's new file 2. Now, according to this, the modification timestamp is supposed to be inherited, and it appears that it was inherited from the file that we copied it from. And it looks like the accessed and birth or created timestamps were set to the current value. They were updated. This follows what we're seeing here. This also is a bit strange if you think about it, because what we're looking at is a file that was modified before it existed, right? It's modified at 1:41 a.m., yet it was created at 1:43 a.m. So if you ever see this, and you will when you're doing forensic investigations, this is a very clear indication that the file was copied from somewhere. So the next thing we're going to do is the exact same thing, but using CMD. So in this location, you'll notice new file and new file 2. Let's go ahead and copy newfile.txt to newfile3.txt. So now we've got a third file. It appears that the date modified timestamp was again inherited, and that date accessed and date created were set to the current value. So it looks like the same behavior, whether or not we used Windows Explorer or cmd.exe. Now, when we get to a latter part of the video and cover analyzeMFT, we may actually see a difference because analyzeMFT is actually going to show us all of the timestamps, standard information, and file name. So the next operation we've actually already performed, which is file access. And again, the registry key you see at the bottom of your screen is responsible for that. If you do change that particular value, then you can enable timestamps by setting it to 0 instead of 1, but by default, that is not the case. So in the next part of the video, we're actually going to use Timestomp and change a file's date and timestamp. So let's go ahead and move over to that part of the video next. Okay, so let's take a quick look at a common anti-forensics tool called Timestomp. Timestomp will enable us to arbitrarily set the MACB timestamps of any given file to any value of our choosing. Now, one quick point of note, instead of MACB, Timestomp actually refers to the values as MACE, M-A-C-E. As a refresher from the beginning of the video, that stands for Modified, Accessed, Created, and Entry Modified, which corresponds to MABC for the MACB timestamps. This utility and others like it have something in common, in that they can only modify $SI, or standard information timestamps. They do not modify and cannot modify $FN timestamps, which means that if we have a given file that we suspect has been time-stomped, we should be able to actually compare the $FN timestamps with the $SI timestamps and find an anomaly. In fact, when we run our demo, we're actually going to do that in the next section of the video using analyzeMFT. Before we actually get started, let's take one quick look at prefetch because I want to show you something as a side note. Here we see a prefetch file exists for timestomp.exe. Because of this, we know that timestomp has already been executed on this system at least once, by virtue of the fact that this prefetch file exists. If we look at the timestamps associated with it, we see that date accessed and date created are 2:38 a.m. and date modified is 3:02 a.m. We can conclude from this that timestomp has been run at least 2 times. We don't know the number of times, but we know more than once. So we could actually parse this prefetch file using any number of different utilities and find out more information, including the exact number of times it had been executed. So if you haven't watched the Introduction to Windows Forensics video where we covered this and other artifacts showing evidence of application execution, I would encourage you to do that. But back to the demo, the next thing we need to do is actually create the victim file that we intend to timestomp. So we'll just call it victim.txt and put some gibberish in it. So now that we've got our victim file, let's go ahead and run timestomp against it. So to do that, we'll run timestomp specifying the MACB directory and the victim text file. We're going to use -z, which will set all 4 MACE attributes. So we'll actually set it to, I don't know, how about Monday, July the 4th, 2016 at 3:33 p.m. So when we do this, you will see that it immediately changes to 3:33 p.m. on 7/4/2016, and it's just that easy. So again, only the standard information timestamps, which is what we're seeing in Windows Explorer, have been updated. And in fact, the hidden one, the one you're not seeing here, which is the C in the MACB, which of course indicates MFT entry modification, has also been modified as a result of this because, again, we told it to set all 4 attributes. So in the next section of the video, we're going to take a look at analyzeMFT, and we'll actually take a look at this particular file so we can see some evidence of timestomping. So let's go ahead and move over to the next section of the video. Okay, now let's talk about analyzeMFT, which I had previously mentioned. AnalyzeMFT is a Python utility that's designed to parse the master file table from an NTFS volume and output the results in several formats, including a CSV format that we can then easily take into Microsoft Excel and sift through and analyze and sort. Now I've got the GitHub page pulled up for this particular project, and I will include a link to it in the video's description. This utility is going to allow us to see a couple of things that we previously mentioned. Number one, not only will we see the $standard underscore information or $SI timestamps for all of the objects in the MFT, but also the $file underscore name or $FN timestamps for all of the entries. This should allow us to look at the victim.txt file that we timestomped in the previous section, and through that analysis we should see that the $FN timestamps do not match up with the $SI timestamps. So let's go ahead and grab the MFT from this particular VM. I'm going to use FTK Imager, though there are several different ways to grab the MFT. Let's go ahead and add evidence item, and we'll add the logical drive, C partition. Now let's drill down into the root of the C drive, and we should see $MFT. Notice you also see $MFT mirror, which is a partial backup of the MFT. We're not going to worry with that right now, just $MFT. I'm going to right-click and click Export Files and stick it on the desktop. This should only take a few seconds to export, and it looks like one file has been exported successfully. So let's minimize all of our windows. And now looking at the desktop, the interesting thing is I don't see $MFT anywhere. Let's bring up a command prompt and change into the desktop directory, and still we don't see it. But if we run the attrib command, you can actually see $MFT is right here, and it has two attributes set, system and hidden. Let's go ahead and remove that. And now $MFT should appear on the desktop. For simplicity's sake, we'll go ahead and rename it to just MFT. Now what we can do is take this MFT file and copy it over to our Sift Workstation, which we'll use to then run the analyzeMFT script. When we run the script against this particular MFT file, we'll then take the results back over to macOS and open it in Microsoft Excel, and then look through the data that we've collected. So let's go ahead and move over to our Sift Workstation next. Okay, so here we are on the Sift Workstation. On the desktop, I've got the MFT file that we copied over from our Windows 10 VM. By the way, if you're not familiar with Sift, that's the SANS Investigative Forensics Toolkit, which is actually available as a script that you can run on Ubuntu 16.04. And it will pull down a large number of free digital forensics and incident response utilities, one of which happens to be analyzeMFT. Now keep in mind that you don't have to run analyzeMFT on a Linux box. You can run it on anything as long as Python is installed. So let's go ahead and run analyzeMFT-help and look at the available options. We're going to have a pretty simple use case, and then we'll use the -F switch and specify the input file, -O and specify the output file, which will be output.csv, and let's also use -E, which outputs the timestamps in Excel-friendly format. So I'm going to go ahead and run this, and I can tell you it will take several minutes to run. So what I'm going to do is cut the video here. When this is finished, I'm going to copy the CSV file back over to macOS and go ahead and parse out the data that we're interested in looking at and then open it in Microsoft Excel. We'll then pick up the video from that point and take a look at what we can see from the analyzeMFT results. So let's go ahead and switch over to macOS now. Okay, as a quick recap, I took the output.csv file generated by analyzeMFT and copied it from the Sift Workstation to macOS. I then used grep to filter out only the entries pertaining to the 4 files we were working with throughout our demo, and wrote that data to output_filtered.csv, and that's what you're looking at here. If we scroll across the top, you'll notice a large number of column headers. We're going to ignore most of these for now, only focusing on the timestamps, but you'll notice it goes all the way here, ending with the rightmost ADS or alternate data stream column. Here are the 4 MACB timestamps associated with $SI, and here are the 4 MACB timestamps associated with $FN. Now, a couple of things to keep in mind. First off, this is not in the MACB order. This is actually the B, this is the M, this is the A, and this is the C. Also note that these timestamps reflect UTC, whereas when we were doing the demo, we were looking at the time in Eastern format. So make sure to apply the 4-hour offset of -4 when you're doing the timestamp conversions, and you'll see that they do match up with what we saw earlier in the video. I went ahead and highlighted a few things of interest. First off, note that new file 2 and new file 3 are both copies of new file, but the difference is new file 2 was copied using Windows Explorer, new file 3 was copied using copy from cmd.exe. you'll notice that in both cases, the creation dates and the access dates reflect the time the copy operation occurred. The modification date was inherited from the original. So all of that makes sense, but the C in the MACB, which pertains to the MFT modification, is different on the one copied with copy from cmd.exe, as are all 4 of the MACB timestamps stored in $FN. They all reflect the time the copy operation occurred. If you look one line above it, that is not the case for the copy originated with Windows Explorer. So just something to keep in mind. Then lastly, of most interest is our victim.txt file, which was timestomped. You'll notice that these timestamps don't even look like the other timestamps. The resolution is wrong. Windows uses a very high resolution of the number of hundreds of nanoseconds elapsed since January the 1st, 1601, which, by the way, is the start of the Gregorian calendar, if you were wondering. So you'll notice immediately something stands out here. If we look at the $FN MACB timestamps, these are the true timestamps, the ones that don't lie because they're only modifiable by the Windows kernel. So our timestomp tool happily stomped these timestamps, but it couldn't do anything about these. So now we can clearly see that this file was not actually created in July of 2016, but rather in August of 2017. So very neat stuff there. One other point of note before we move to the final section of the video. Earlier I had shown you this table, which is really an oversimplification of a few common file operations and what happens to standard information or $SI timestamps. It's a bit more complicated than that in reality. If you look at this particular article from November of 2010 called Digital Forensics Detecting Timestamp Manipulation, if you scroll down, there's actually 2 tables here, $standard_info and $file_name. Both have different behaviors with regards to how timestamps are updated. For example, file modification does not actually result in any of the MACB timestamps being updated in $FN, but it does in $SI for modification and accessed. So that's just something to be aware of. It's, again, a bit more in-depth than what I was trying to cover in this video, but you may want to read this and be aware that some of the $FN timestamps may not be updated the way you think they may. That's because Windows does not update $FN the same way it updates $SI. In fact, I believe, here's the quote right here. It actually says from the Carrier's File System Forensics Analysis book, Windows does not typically update this set of temporal values like it does those with the standard information attribute, as they frequently correspond to when the file was created, moved, or renamed. So again, just something to be aware of. Okay, so let's go ahead and move into the final section of the video. We're going to switch back to the Windows 10 VM, and I'd like to show you a couple of things I noticed recently when using the new Bash on Windows feature. So we'll go ahead and switch over to that next and wrap up the video. Okay, the last thing I want to show you is how Bash on Windows seems to affect these timestamps. You'll see here the same MACB folder we were looking at earlier, and I've created 3 new files. Oddfile.txt is just a new file I created at 1:28 a.m. 1 minute later at 1:29 a.m., I copied oddfile.txt to oddfile2.txt using Windows Explorer. As we expect, date accessed and date created reflect the time the copy operation occurred, and then the modified time was inherited and shows 1:28 a.m. Then 1 minute after that, I copied oddfile.txt to oddfile3.txt using the copy command from cmd.exe. As expected, date accessed and date created reflect the time of the copy operation, which was 1:30 a.m., and date modified was again inherited. Now we do know that behind the scenes, the timestamp we're not seeing here, which is the C in MACB relating to MFT entry modification, is different, as are all 4 of the $FN timestamps when we copy something from CMD. But that aside, now let's see what happens if we do the same thing with Bash. So I'm going to click in the address bar and type in Bash to spawn a Bash window. And then what we'll do is go ahead and copy oddfile.txt to really oddfile.txt. Now we know that what should happen is that it's currently 1:42 a.m., so date created and date accessed should be 1:42 a.m., and date modified should be inherited. The only trouble is it's not inherited. All 3 timestamps are 1:42 a.m. Now, I haven't seen a lot of information about this online. In fact, there's very little information about Bash on Windows Forensics at all. But I'm sure I'm not the only one to discover this. What I'm going to do next is I'm going to re-export the MFT, take it into analyzeMFT again, and then look at all of the timestamps associated with reallyOddFile.txt. So I'm going to cut here, we'll come back, and we'll look together to see what the behavior is with the $SI and $FN timestamps for reallyOddFile.txt. This is the first time I've actually done it, so we'll both see the results together. So we'll cut here, come back and look at that, and then finish up the video. And now for the exciting conclusion. So I've rerun analyzeMFT, and we are specifically looking at these 4 highlighted files. To recap, oddfile.txt was a newly created file. Oddfile2.txt is a copy of oddfile.txt using Windows Explorer. You can see that the creation and access timestamps reflect the time the copy occurred and are as expected, and the modification date is inherited as expected. Oddfile3.txt is a copy of oddfile.txt using cmd.exe with the copy command. Again, the creation and access timestamps reflect the time the copy occurred, and the modification timestamp is inherited as expected. And then reallyOddFile.txt is a copy of oddfile.txt using the bash command prompt. This is what's not expected, in that the modification date is not inherited, as we saw in Windows Explorer. And you can see that all 4 of the $SI timestamps reflect the exact same time, the time the copy occurred. And if we scroll on over, all 4 of the $FN timestamps also reflect the same time value. So that is interesting. That is not what I expected to happen. I'm sure I'm not the only one that has discovered that. And again, I think there's plenty of room for some Bash on Windows forensics and more research into this topic. It's expected that Bash on Windows is going to come out of beta in the next Windows release, so I'm sure we'll see more widespread adoption of that and more of a need for forensics on that side of the house as well. Well, that wraps up this video. I want to thank you very much if you've made it this far. Thank you for watching the video. I hope it's been informative. We tried to cover a good bit of material in a relatively short amount of time. I'm not sure which video I will create next, but I intend to continue the Introduction to Windows Forensics series. If you have a specific topic that you would like me to cover, please do let me know. You can follow me on Twitter at DavisRichardG as well. I would greatly appreciate any likes or subscribes or any sharing of the content on the channel, so please feel free to share the videos and tell others about them. The whole intent here is to give back to the information security community and share the knowledge. So again, I hope this has been informative. Thank you for watching, and I'll see you next time.